Hello, I'm Patrick, and this is Lab 5, and I'm going to be going over magnetic braking through Faraday's law. Our objectives here are to gather observational data as we conduct an experiment in order to observe a bar magnet as it falls through a conductive aluminum foil tube. Next, we will then stimulate the same experiment employing glow script to model the magnet-tube interaction computationally. We will then compare our stimulated predictions with the data we observed in the experiment. Key to our investigations are some physical principles, including the Biot-Savart law, Faraday's law, and Newton's second law. Just previewing our results, we end up finding an average experimental fall time for the magnet of 1.26 seconds and a slightly faster computational fall time of 1.166 seconds. So principles of physics. In order to fully understand magnetic braking, we're going to discuss the core principles of physics a little more. The Biot-Savart law provides us insight into the magnetic field generated by electric currents. Faraday's law bridges the gap between changing magnetic fields and induced electromotive forces. The respective formulas can be found under its name. Finally, and as usual, Newton's second law stands as the bedrock of our motion, correlating force, mass, and acceleration. These principles form the basis of our understanding and allow us to complete this simulation computationally. So here's our experiment. First, let's get to our experiment. Our system consists of the aluminum foil and the bar magnet, with everything else, the earth, air resistance, and beyond, constituting our surroundings. As we set the stage with initial conditions, we will imagine and treat our bar magnet as a magnetic dipole. For the measurements, the tube's length was found to be 35 centimeters, its width was 0.6 centimeters, and the magnet's mass at 25 grams, with inner and outer radii then calculated. These measurements are pivotal, as we will use them to set up the parameters for our experiment. So the experimental results for part 1, by averaging 5 trials, we can determine the average drop time of a bar magnet, a key observational data point. Our observations determined a consistent average drop time of 1.26 seconds. Here are our individual trials, showcasing the slight variations in times that collectively contribute to our average. So for our simulation, the second part of the lab, we had to computationally create a simulation that modeled the experiment we conducted in the first part. We've cut out excerpts of the most important parts of the code into 3 primary sections on the slide. The first block of code in the top right is where I went through and set up the initial conditions and variables I had measured in the experiment. These variables are crucial, and in the second block of code on the left side, you can see where I went through and set up the magnetic field of the bar magnet, as well as the change in flux over time in the lower part as the magnet fell through the aluminum tube. The third block on the bottom right slide is where I calculated the induced current as aluminum foil in the aluminum foil, as well as its magnetic field for the simulation. This code ran and output the results on the next slide. And here's the results from our simulation. So our computation in the closer code gave us a stimulated drop time of 1.166 seconds. This slight discrepancy from our experimental results could be attributed to variations and errors inherent to our physical trials, as well as ignoring other forces acting on the bar magnet, such as air resistance. We must remember that accuracy often hinges on the number of trials. Additional discussion. So, what if the resistivity of the conductor were reduced as close as possible to 0, and how would the dynamics of the falling magnet change? Well, this would cause the induced current in the aluminum foil to increase, which would then cause the magnetic force to also increase. This would ultimately cause the magnet to fall slow through the tube due to increased force or resistance against gravity. The second question asks us, if holes or slots were cut into the tube, how would this affect the ring currents in your model? Well, any of these holes or slots would disrupt the induced current, which would in turn cause it to decrease. This would then also cause the magnetic force to decrease, which would ultimately make the magnet fall faster through the tube. So these two situations basically would have the opposite effect on the bar magnet. And this is Lab 5. Thank you for your time.